let's go. Cameron, you're done there? All right. So, the question, well, let's do this. Let's answer these questions here first, and then we can talk about the quiz. So,
are you wearing green? No. Has anyone pinched you? No. You're my first pinch of the day. There are two people, and I'm just like, they asked me not to. No, if they're not wearing green, green eyes don't count. Wait, what about your bracelet? Your bracelet? Oh, you're good. Pinch me back.
all right.
Oh, good. I know my shoes are blue.
So let's talk about Euler's method. If we're gonna, we'll come back to this later here, so you don't have to worry about jotting this down. But if we're talking about the quiz, down at the bottom there, Euler's method. Basically, two things you have to be able to do with Euler's method, and that is either if there's less than 10 steps, you write it out, and if there's 10 or more steps, you just trace on the calculator. So you graph the differential equation with the step size, and you just trace to that value you're looking for and just write it out. That's all you got to do. Okay? So, let's do one now. The question came up on number 6. Okay, on number 6. So in every Euler's method problem, you're going to be given this information over here on the right, or you can figure out this information on the right. You've got to be given some differential equation. You've got to be given some initial condition. You've got to either be given or figure out the step size, the delta x, and then you're being asked to find some value, some other value on the y graph. Now, the y could be p or some other letter, like in number 6, the y value was p. So in my table, instead of y, this would be p, and this would be, I mean, when you make your table on the quiz, if the function has p in it as the y value, or the output variable, and you put y in your table, that's fine. I'm not going to count that off, because you do have to use y and x in your calculator. Actually, y1 and x in your calculator. And delta y would be delta p, and the new y would be the new p, or whatever. I mean, so understand that. And t might be the input variable instead of x in your difference equation. Okay, so the comment was made that there, on number 6, when you did the table, it was all zeros. Why? Why? You had to go back to the problem, right? Did you go back to the example? What was the example about? What did the P stand for? The population of what? Of the flies. And in their example, they started with P of 0 equals 1,000, right? But in problem 6, what did they give you? P of 0 equals 0. What's that mean? What does P of 0 equals 0 mean in this problem? You started with 0 flies. So after 5 days or whatever, how many flies do you have? 0. That's why it came out all zeros, right? Because there are no flies. And so you can't, I mean, I don't want to get into the whole sex education thing here, but if you start with 0 flies, there will be no flies after 5 days. And so that's, well, I mean, that was what it was about, right? That's why. So if you got all zeros, you were doing it right. Okay? You were doing it correctly. Okay? Now, number 8. So sometimes the simplest problems are the most confusing because you're getting weird things that you don't expect, even though you're doing it right. And that's kind of the way 8 was too. They gave you a differential equation of what? Y prime equals 3, right? Well, that's a real simple differential equation, right? That means the slope is always 3. It's just a line, right? So we actually could solve this. Well, what did they first ask in number 8? What was 8a? Just to solve it? Yeah, write the exact solution. So if they want you to write the exact solution, that means it has to be one we know how to solve, just like an antiderivative. Or it could be the one we memorized. I might ask you, to write this one, y prime equals 3y. Right? That's that one we said where the solution is y equals ae to the kt. right? That's the one we've just looked at. And if it's one like this, then the solution is just that. Okay, so, I mean, that's something we've done in the past. You still should be able to do it. So you might review that one. Probably won't ask you about Newton's law of cooling to make sure you do that. But this one, the y is just going to be what? What's the antiderivative of 3? 3x plus, well, c. And then they gave you an initial condition, right? What'd they tell you? Y of 0 is 2. So that tells you the c is actually going to be 2. So that's the exact solution, right? And then what they ask you in the next part? Was that all they asked you in part A? Write the exact solution? What they ask you in the next part? So you're going to do y of 1, y of 2, y of 3, so you're going to do all those steps of the table. And the step size is what? They said step size of 1, so they just told you that. Okay, so that means I'm going to start at 0 and then do 1, then do 2, and then do 3, and then do 4, and whatever, right? And so what is the y? Well, the first y they said was 2. What's y prime in this problem? Always 3. We don't have to plug anything in. Y prime's always 3 in this one, which is an unusual one because it usually wouldn't be that way. How do we find delta y? Y prime times delta x. It's rise over run times run. Rise over run times run. That gives you the rise. Okay, delta y, we call that the rise. That means if we go over 1, how much are we going to go up? If we go over 1, how much are we going to go up? This problem, every time you go over 1, you're going to go up what? 3, because the slope's 3 every time. So your rise, since our run is 1, our step size is 1, then our slope times 1 is going to be 3. Our rise is going to be 3 every single time. So our new y is 5. And then our slope is 3. We're going to go up 3. We're going to get 8. 8, our slope is 3, we're going to go up 3, our new y is 11. Slope is 3, rise is 3, new y is 14, right? Whatever. And then it's just a line, I think, right? And what else did it say? What else did it say? Did it say verify or anything like that? What accounts for the accuracy of Euler's method? So now this is Euler's method right here. Oops. This is the exact solution. So plug a 3 in. 3 times 3 is 9. 9 plus 2 is... right. Oh, I plugged in a 3, I got 11. Oh, Euler's method was supposed to be an approximation, right? How come it's exact? Oh, because it's a line. Because what does Euler's method do? It assumes, when you calculate that the slope is 3, what's it do? It assumes when you step over 1, it's going to stay 3 that whole time. Most of the time, it doesn't stay 3 that whole time. The slope is changing. But is it in this problem? The slope isn't changing. It assumes, this is like a flat graph for a left rectangle, right? Left rectangles fit a horizontal line perfectly. Well, Euler's method is going to fit a line perfectly, right? Because it assumes it has the same slope the whole time, and a line does have the same slope the whole time. Okay, so 6, kind of a weird situation. 8, kind of an unusual, or not unusual, but I guess a very specific situation that is happening. Okay, and so we had a request here to go through one more in the table, just kind of from scratch, so 11 might be a good one. So 11, you had the differential equation, 1 plus t minus y, is that correct? And you were given y of 0 is 1, and did they tell you the step size? That was nice of them, but they might not have. What are they asking you for at the end? Y of 2. So let's pretend that they hadn't told us the step size, because I probably will not. Maybe I give you a couple different problems, and then one I might not. But for sure, there's going to be one where I'm not going to tell you the step size. So how would I get the step size here? What's the, yes, b minus a over n. What's the b, what's the a, what's the n here? Okay, we're going from 0 as 0x value at the beginning, and we want to find a 2x value. That's from 0 to 2. So 2 minus 0 divided by how many steps? They want us to do 5 steps on part A. They want to use 5 steps. So they went ahead and said use 5 steps of 0.4 size. That was nice of them to go ahead and do that calculation for you. But they certainly wouldn't have had to. You should have been able, once they told you 5 steps, you can find the step size, right? It's 0.4. Okay, so with that information, I usually go ahead and fill in my table right here right away. Okay, I go ahead and just do this part right away, so I don't lose track of that. Sometimes you go through that first line and then you're like, oh wait a minute, now how's this next line start? You kind of forget. Oh yeah, it's because we're going over 0.4 every time. You kind of forget about the step size. So once I calculate the step size, I usually fill in that table. Starting at 0, going to go down to 2. Okay. All right. So what goes in here? 1. Right? Y of 0 equals 1. So my starting point is 0, 1. What goes in? Now you guys got to memorize how this table's lined up, right? You got to remember. You got to know. You got to be able to build this table, right? And go through and show this. All right. So what's y prime? 0, because you're going to plug into this. So you're going to put a 0 there, and you're going to put a 1 there. 0 in for t. Because right here, that's actually, this column is actually t. T is your input variable, y is your output variable. Right? How do I know y is the output variable here? Other than y is almost always the output variable, but how do I know y is the output variable? Because of the y prime, right? We only do primes on the output variables, right? So p prime, you have p prime, p is the output variable, right? And t's got to be the input. So t is the input. So right here, I'm taking these two values and plugging them into my differential equation. Some differential equations only have y in them, so you only plug in a y. Some differential equations only have an x, so you'll only plug in for the x. Some have both, right? And some don't have either, like this one. The y prime was just 3. It was constant the whole time. So we put a 0. That answer that? Okay, so we put a 0 in for the t, put a 1 in for the y. So 1 plus 0 is 1, 1 minus 1 is 0. So we get 0. How do we get this column? That's the rise, slope, times step size, right? Rise over run times run. Our run every time is 0.4. So slope times 0.4 is 0. So our new y is our old y plus our rise. So we went over 0.4 and we're going to go up nothing. So we're still at a y of 1. So we are now at, and then that goes down to here. So we're now at 0.4 over, and we're still at 1. Okay? All right, and now we calculate a new slope. So now what's my slope here? I went over 0.4 and I'm at 1. What's my slope now? So now we put in 0.4 for t, and we put in 1 for y. So we got 1 plus 0.4 is 1.4. Take away 1 is 0.4. So my slope is 0.4. So I got a new slope now at my new spot. Now, what's my rise? 0.4 slope times a 0.4 run gives me a 0.16 rise. So if I move over 0.4 again, I'm going to go up 0.16. So where am I now? 1.16. I'm now at 1.16. Okay? And so that comes down to here. So now I moved over another 0.4. So now I'm at 0.8 and 1.16. And then we just keep going. Okay, so now my slope, 1 plus 1.1, no, I'm sorry, 1 plus 0.8 minus 1.16. What is that? We'll do one more line here. 0.64. And then to get my rise, I'm going to take 0.64 times 0.4. 0.256. And then my new y is my old y, 1.16, plus my rise, 416. Okay, we keep going, and at the end here, we're going to get 2.07776, 3 sevens. And then I can copy that down here. I don't really have to, but I just like knowing that it's that. And we usually only go 3 decimal places. You want to keep more decimals through here, so your last one is accurate. So keep them on your calculator. So there we go. So we got the point. Y of 2 is 2.078. And we got it. Yes.
So on the quiz tomorrow, if we have to put like a final answer is y of 2 equals 2.078.
That is your final answer.
And we have to round the 3 decimals.
Anytime you give a decimal answer, it's got to be accurate to 3 decimals. Yep. Okay? That's it. So if I give you single digit step size to do, this is what your problem would look like. Now, part B, they said use what? 10 steps? So where do we go for that? We go to the calculator, right? So let's get that out, and let's check that out one time. And we're going to plug this in. Now we got to remember that anytime we put in a differential equation, and we can tell that by when I go into my graph entry, yours is probably still in differential equation mode since that's where you left it, so that's good. And so I'm going to type in 1 plus, what am I going to put for the t? I've got to put x plus, minus, and I've got to put y 1. So instead of 1 plus t minus y, I've got to put 1 plus x minus y1. And you can remember that by looking at down here at this initial condition. You've got x and you've got y1 is the variables that they want you to use in the calculator problem. Okay, so your output variable, you've got to put y1, and your input variable, you have to put x when you go to your calculator. Okay, what else do we fill in on the calculator?
0 and 1.
The initial condition, 0 and 1. And what else?
Step size.
And where do we go for that?
3 dots.
The 3 dots. Go over here to the 3 dots, and we got to put the step size in. So that is down here, and it was what? I guess we could put 0.4 and just check our other problem, but let's do our new problem. Our new problem is a step size of what? 2 minus 0 over 10 steps, right? What's that? 0.2, 2/10. 0.2. So our new problem, 10 steps, is a step size of 0.2. So we need to put in 0.2 and hit enter. Okay? Now, we came out, some of you guys were saying it, and I wasn't. I don't think I was catching on. You were talking about Zoom Fit was working, and I kept trying to do Zoom Fit and put in the X's. You don't have to put in anything. Just do Zoom Fit right away. It actually works well. Somebody in their class said it, and I finally understood what I think you guys were trying to say. Just do Zoom Fit, okay? Just do Zoom Fit. Now that's actually weirder than I thought it was going to be. That's not what yours looks like. Oh, well, so my here I thought I had figured out. Did I type that in right? 1 plus x minus y1. Try Zoom Fit again. 0.2, so that's all okay. Zoom. I know. It's weird. Well, to be honest, I don't think it really matters, to be honest with you. Because what do we have to do? We have to go to trace, right? All we really need, doesn't really matter what the graph looks like. We really just need to trace, okay, and go to 2, right? You can right arrow or you just type in a 2. So we just need to get to 2. Okay, so to be honest, what the graph actually looks like is really not a major concern here, as long as you just trace and get it. So Zoom Fit seemed to be working. I'm not sure why mine was looking different than yours, but we're getting 2.107, is it? And what should be happening is that's actually a better approximation of y of 2 than the one we had with only 5 steps, 2.078. This is actually probably a little better approximation. Okay, we don't know what the exact values of this. And then did they also have, you were supposed to verify that something was a solution? So let's talk over that. That'd be the last thing you would do with these problems. Verify something's a solution. So they gave you this differential. Here's our differential equation right here. Right? And we want to show that our proposed solution, what they give us, t plus e to the negative t. They said that that is a solution. Now remember what you're doing. If I tell you that x equals 4 is a solution to this equation, right? What do? Well, you put a 4 in, and you show that, yep, it is a solution. You plug in a 4. That is the solution. So what we want to do is plug this into this. So in place of the y over here, we're going to put, this is y prime right here. So in place of this y right here, I'm going to put t plus e to the negative t. And what am I going to put on this side in place of y prime? The derivative of y. So over here, I'll do the derivative real quick. Derivative of t is 1. Here I'm going to kick out a negative 1, so that's going to be negative e to the negative t. So my y prime is 1 minus e to the negative t. So now I'm trying to show that these are the same, so I'll just distribute this negative. So I get 1 plus t minus e to the negative t. The t's cancel, and I get 1 minus e to the negative t. Sure enough, those two match, and so that is the solution. So that's what we did back in chapter 2 when we were doing differential equation work back then, verifying that something's a solution. So it's very much like an algebraic equation. Show that 4 is a solution. You plug in a 4, right? Remember, you always take your proposed solution, you plug it into the differential equation. And remember, a solution to a differential equation is the original function. So this is your proposed solution right here. They want you to show that that is the original function. So you take that and you plug it into the differential equation. So you plug that in for y, and then you'll plug the derivative of that in for the y prime, and then just show that the two sides are the same. That's it. Okay? And then we could double check. Did they ask you to check the actual value of y2 then? Did they say that at all? The actual value of y2, do it on your calculator for me real quick. Just plug a 2 in for t then into this y right here. Just plug a 2 into the actual function. Let's see what that is. Give me a decimal now. So it'd be 2 plus e to the negative 2, which would be 2.135. So that's the actual value of y of 2. Okay? And we were getting 2.078. Then we got 2.107. So we were getting closer. Right, 20 steps, we'd probably get a little closer yet. 30 steps, we'd get a little closer yet. And we can do that on our calculator with Euler's method. But so we're doing an approximation of the solution of a differential equation, which is the original function. So when we find y of 2 on these problems, or y of whatever, we're using Euler's method to give us approximate solutions, approximate values on the original function. Okay, but if we know the actual solution, the actual original function, we can find those exact values. Okay, and so it's just kind of a close cousin to what we were doing with areas. We can find an exact area, great, but if we can't, we can do right, left, trapezoid, midpoint approximation, Simpson, that are approximations to that area. The more subdivisions we do, the better the approximation is. Okay. And then, of course, we went an additional step with areas, and we talked about error. How much are they off? And what is the error, and what's the max error, and all that. And we'll review that here in a second. Okay? All right. So, the quiz. Let's go through that here real quick then. Okay, so that. All right. So, we talk about the things that the quiz is about. I suppose maybe I go to this page. Probably should have this page first. Okay, so maybe we can copy these things down, and then we'll go through them and talk about them in a little more detail. So, what do you have to be able to do for tomorrow? So, section 6.1 was where we investigated more with the left, right, midpoint, trapezoid, and Simpson. We wrote those new ways of writing them, where we took the b minus a over n out in front. Took the b minus a over n out in front, and then f of x sub 0, f of x sub 1, for left, for right. Trapezoid, we had 2 of everything except the ones on the ends. Simpson, we had 4, 2, 4, 2. That was one version, and I've got those up here again. I don't think you want to rewrite it now. I mean, I'll put it up later if you want, but you've got those in your notes already. But so you need to be able to draw some, probably give you a graph and have you draw me some midpoint rectangles or something, whatever, shouldn't be hard, and I draw a handful of them maybe. write out if it's less than 10, right? And I'm not going to give you any that are over the 10. You know, remember we had that area program where we could go in and we could do, you know, big deal. You can just type in, run that program, type in the right numbers. I mean, so I don't think that's going to be on a roll. You say, well, that'd be easy. That'd be a good question. We've had some issues with that program sometimes, so I don't want to get into that. So don't worry about any, you know, doing an S50 or something, right? I'll just give you a small number. So probably have to do some of those. And then also in 6.1 we talked about over under, right? The concavity, we'll go through a slide here and review that. But the over under approximations, we'll be able to talk about that. We did some of that true false stuff. Must be true, might be true, can't be true, that kind of stuff. We did there. Okay, section 6.2 is all about those error formulas, right? The K1, the K2, the max F prime, the max F double prime, that stuff. Always round up a little bit, right? If you graph your F prime, find the highest point, and it's 2.137, then you might use 2.14 or 2.138. You would always, right? It's supposed to be a worst case scenario, so you put that number in the box, and you find that max error. Okay. And then, of course, what we just talked about with Euler's method. We did everything you'd have to do with Euler's method today here. Okay? That's pretty much everything. All right. So as we go through each one of those, and then I'm going to, at the end here, I'll give you some problems that you could go back and do. Some of them would be repeats of some homework problems you did. Some would be new ones that are just like homework projects you did if you want to. Totally up to you if you want to go through and do any of those. The rest of the period here. So, I'll put those up here in a second. Okay, so that, again, I'm not going to leave that up long enough to write all that out. That's just, and we've done that before. Okay, so your left, B minus A over N, you got, starts at the left edge and you stop one short. The rights, you know, you go one over and then go to the right edge. Your midpoints, your trapezoid with the 2-2-2 pattern in between there, and then the 4-2-4 with Simpson if you want to do that. Remember, Simpson's always going to be even, 8, 6, 4, something like that. We also have these shortcuts, right? If you want to do a T4, that's the same as doing an L4 plus an R4 and divide by 2 if you want to do that. Or Simpson, if you're going to do an S8, you can do 2 M4s plus a T4 and divide by 3. Or you can write it out the other way, right? So you want to be able to do those. If you want to use those, you can, or you can use the ones on the previous page. It's up to you, but we do have these averaging ways of doing trapezoid and Simpson. Okay?
Will any, formulas be given to us?
The error formulas. The error formulas will. Okay? So, of course, we talked about if it's increasing, if a graph is increasing, is how you tell if left or rights. So an increasing graph, lefts will be under, rights will be over. With a decreasing graph, it's the opposite. Lefts are over, rights are under. Concavity is the key here. Concave down, trapezoids will be under, midpoints will be over, because remember, midpoints have pivoted trapezoid. Concave up, midpoints are under, trapezoids are over. So, you know, that kind of thing. So we had some of those kind of questions. And then we got into 6.2. That was the error bound. So if I ask you for the error bound, what I really mean is just the max error. Technically, the error bound would be that whole statement there. But I think on the quiz, any of those problems, I'm asking you for the max error. Or if I say find the error bound, I just mean this number here, right? This number here on that formula. And the formulas are there, and those will be given to you, right? Those will be given to you in the problem that you're doing. So if you're doing lefts or rights, you're finding this K1 value. Remember, it's F prime. You graph F prime, do a zoom fit, right? So if we're doing the integral from 0 to 2, do a zoom fit from 0 to 2 is a good way to do it, but you want to find that max value. Remember, it's positive now, so if you got 4 up here and negative 6 down here, what are you using? Using 6, right? If it comes out exactly 6, that's good. Use 6, but if it's a decimal, bump it up a little bit. Okay, so that's how you find K1. If it's K2, you're doing the second derivative, and then you're doing the same thing, right? You're finding the max value, and that's what you're putting in there. That's for midpoints and trapezoids, right? And I think I'm probably going to put the formula right with the problem, so you shouldn't have any problem getting the right formula. But just remember, K2 means second derivative, K1 is first derivative. Okay, and those formulas will be given to you. And then, of course, don't forget you got the type of problem where I say, hey, I want you to find how many n's does it take to be within 0.005. So I might actually give you this value, and then you have to find the n. You have to solve for n, right? So it might give you that value and you find n. Or I might just want the max error. Okay, I'll say 10 rectangles. How much error is there for the max error? Okay, that's it. That's it. Okay, so here's some problems. If you want, like 10 and 12, like we just did 11, and on your homework you had 13, you had 15. There's 10 and 12, they're the same thing. I mean, Euler's method, so if you want a little more practice doing the table on Euler's method, there it is. I will be here in the morning. I won't probably be here when you guys start to test, but I will be here in the morning if you have questions. On anything, but some of those are ones we did in the homework. Some of them were like ones we did in the homework. So if you want to go review and do any other problems, I just picked out some that might work. Okay, and then for when we come back from spring break, so you can start on that today if you want. If you feel good for the quiz, we'll start on that. You can do that tomorrow after the quiz. This is definitely be something you can be working on. Okay. Sample 3. The next multiple choice section. And then 1 and 2 in the free response section. Okay. So you can the next the 29 through 45 multiple choice is calculator problems, and I think 1 and 2 on the free response are calculator problems too. No, on the actual on our final, I'm going to do it because they changed it a couple years ago, and I've been doing it kind of consistently every year this way, so I'm going to continue to do it this way. We're going to do 3 multiple of the free response. 3 will be calculator, 3 will be no calculator. On the actual AP test now, they've moved to 2 that are calculator and 4 that are no calculator. But we're going to do 3 and 3, and I think in our packet it's that way. It's 3 and 3. So. Okay, so I'll help you out if you've got questions on these review ones you want to do. I got the answer books here if you want to work on your sample packet some more. Okay. It'd be the same as what's on this sheet. So your 6-1, your 6-2, your 6-2. So this is 381. This is 391. There you go.
First off, you're still recording.
Uh.
And second off, on the